¿Qué va a usar la Valier? No, es que pronto se va a estar moviendo. Checa.
No, I won't have audio. I mean, I have one video that has some audio, but it's better not without the audio.
USB.
Okay. Yes.
You have a clicker, or do you want a clicker?
If you have a clicker,
Okay.
yeah, that would be great.
All right, we're going to get started. For those who are outside, please join us. My name is Zach Al-Belushi from the University of California at Berkeley. And so it gives me great pleasure to introduce our final plenary speaker for this Congress, Professor Joan Redwing. So Joan Redwing is an American material scientist working on electronic and optoelectronic materials, including processing of semiconductor thin films and nanomaterials, specifically by metal organic chemical vapor deposition. She is a professor at Penn State, where she holds the title of Distinguished Professor of Material Science and Engineering and Electrical Engineering. Prior to being at Penn State, she received her bachelor's in chemical engineering from University of Pittsburgh in 1986. She then went to work for GE in the R&D area, working on X-ray targets produced by chemical vapor deposition. She then did her doctoral work under Tom Keish at University of Wisconsin in chemical engineering, where she studied dopant incorporation in gallium arsenide thin films, also grown by metal organic chemical vapor deposition. After her PhD, she did work in industry for some time, specifically working on 3-5 semiconductors for high electron mobility transistors. And during her time in industry, she has co-authored many patents for her work before joining Penn State in 2000, where her group worked on group 3 nitride semiconductors, but also on nanomaterials like silicon nanowires, and now on these two-dimensional materials grown by epitaxy, by vapor phase epitaxy. So at Penn State, she's also the director of the Two-Dimensional Crystal Consortium. This is a National Science Foundation materials innovation platform on the topic of scaling these 2D materials, such as these transition metal dichalcogenides for microelectronics. So this is a national user facility open to many users. So she also serves as the on the editorial of Journal of Crystal Growth. She's an executive editor in 2D materials, but also is the vice president of the American Association for Crystal Growth. So she has won many awards for her contribution in the field of crystal growth and epitaxy. She's also a fellow of the American Physical Society, a fellow of the Materials Research Society, and also a fellow of the American Association for the Advancement of Science. So without further ado, it gives me great pleasure to introduce our plenary speaker. So please welcome our speaker, Joan.
Good morning, everybody. You can hear me fine. First of all, before I start, I want to thank Zach and the other co-chairs of IMRC for inviting me to give a plenary talk here in beautiful Cancun. It's quite an honor, and I really appreciate that. What I'm going to do today is to tell you about two-dimensional semiconductors. So semiconductors have been in the news a lot recently. So most of this is driven by supply chain issues that came about as a result of the COVID pandemic. So there were limitations in the supply of semiconductor chips, right? And in the US, that impacted the supply of new cars, right? So as a result, people recognized that, all right, there's a lot of semiconductor chip technology in our cars, right? Cars are basically computers on wheels these days. And that's only going to increase as we move towards more self-driving automobiles and as artificial intelligence kind of integrates with our daily lives. So for a material scientist, this is great news, right? There's excitement about my field now. And not only that, but there's also interest in new materials that can drive further advances in electronics, in computing, and also in communications. So for those of you who maybe aren't familiar with this field of electronic materials, let me just put things in context for you, where things stand. And I'll do that by using something that you're very familiar with, which is your cell phone, right? So if you think back to the early days of cell phone technology, which was not that long ago, many of you in the room can remember back in maybe the mid-1990s, the cell phones were large, right? They had external antennas, right? And they were used primarily for making and receiving phone calls, right? And then in the 2000s, you could start to use your cell phone to send text messages, right? So this was sort of the advent of the flip phone, also the BlackBerry, they were widely used. And then in maybe the 2010s, the early 2010s, we started to have smartphones be much more widely available. So now you could access the internet on your cell phone, right? And nowadays, everybody is basically carrying around a supercomputer in your pocket that also has a very high performance camera. So all of this evolution in cell phone technology and computing in general is tied to the evolution of the transistor, right? So you're probably aware of Moore's law. So back in 1965, shortly after the transistor was developed and the integrated circuit was developed, Gordon Moore, who was one of the co-founders of Intel, observed that the number of transistors that can be fit onto a square inch of silicon roughly doubled every 12 months, right? And that came to be known as Moore's law, and it's been the guiding principle of the semiconductor industry over the past 50 years. So the improvements in, or the Moore's law has generally been guided by the ability to shrink down the physical size of transistors, right? So what I'm showing here is a plot of the node. So the node is roughly related to the physical size of the transistor in an integrated circuit. And this just shows how the node technology has evolved over about the same time frame as the cell phone technology that I showed you earlier, right? So if we just take a look at the 28 nanometer node, right? So this 28 nanometers, this came about in the early 2010s, around the same time as we had accessibility to smartphones and 4G wireless technology. And then the nodes have been generally, continuing to shrink down to 7 nanometers and 5 nanometers, right? And so the 5 nanometer node is associated with the advent of 5G technology and artificial intelligence. And just to put these sizes in context, a human hair is about 90,000 nanometers wide, right? And human DNA is about 2.5 nanometers thick. Now, if you take a look at this chart that I'm showing here, you can see that now in 2023, we should be down to the 3 nanometer or the 2 nanometer node. But this is where we start to encounter some problems because we're reaching the physical limits of silicon, which is the semiconductor material that comprises all of the transistors we use today. So as I mentioned, we're now getting down to the below 5 nanometer node. And this is a schematic showing the current transistor geometry, which are FinFETs. So these are basically vertical fins of silicon, and the gate wraps around 3 sides of the fins. And you can see that you can shrink down the width of the fin from 7 nanometers down to about 4 nanometers. But the problem that you start encountering is that as you get down below about 4 nanometers, you start to encounter the physical limits of the silicon material. So for example, if we consider the electron mobility, so that's the velocity of electrons in the silicon lattice under an applied electric field. If you take a look at the figure that I have on the lower right, this shows how the electron mobility of silicon changes as you shrink down the thickness of silicon. And it's as a function of the electric field. So you can see that the electron mobility doesn't change very much at 7 nanometers, 5 nanometers, even 4 nanometers. But once you get down below 3 nanometers, the electron mobility starts to drop off quite a bit. And that's just because you start having scattering of carriers that degrades the electron mobility. In addition, as we shrink down the width of the silicon, it also becomes more difficult to turn the transistors off. This is known as the electrostatic control of the transistor, and it's an additional problem that's encountered when you start getting down to these very small length scales. So what's next? How can we continue physical scaling of transistors beyond silicon? So there are a couple different options that are being pursued, and I should mention that no one really knows what the direction is going to be. There are a number of different things that are being pursued. It's a little scary, to be honest, but also very exciting. So there are some different alternatives. So one direction would be photonic integrated circuits. Also, there's a lot of interest and work being done in neuromorphic computing. So that's brain-inspired computing architectures, and of course, quantum technologies, right? But if we want to continue physical scaling of integrated circuits, we need a new material beyond silicon, right? Silicon's not gonna cut it, as we move forward. So this is where two-dimensional materials may play a role. So what are two-dimensional materials? So most of you are probably familiar with graphene, right? It's formed from graphite. It's a single layer of carbon atoms. It was developed in the early 2000s by a group in the UK. They subsequently were awarded the Nobel Prize, and this sparked a lot of interest in this whole class of layered materials. So these are materials that have a layered crystal structure, and I'm showing one of them here. This is moly disulfide. So in a crystal like moly disulfide, you have molybdenum atoms, they're shown in gray, and they're covalently bound to sulfur atoms. They're the yellow balls in this structure. So you have these individual layers with covalent bonds, and then the layers stack and are held together by much weaker van der Waals forces. So it's possible to form a single layer of something like moly disulfide, which we refer to as a monolayer, or maybe a few layer film that has passivated surfaces. So it generally lacks dangling bonds on the surface. And that's ideal for an electronic or an optoelectronic device. In addition, this class of 2D materials offers a very wide range of electronic properties. So it includes things like hexagonal boron nitride. Hexagonal boron nitride has a very wide band gap, around 6 electron volts, so it acts as an insulator. It also includes materials that are semiconductors, like moly disulfide, which has a moderate band gap. There are elemental 2D materials like black phosphorus, which has a narrower band gap. And then that extends all the way to things like graphene, which are semi-metals. So you can see that you have a really wide range of electronic properties to play with in this 2D material system. What I want to focus on today is the material system that we've really been working on. These are semiconducting 2D materials, and these are the transition metal dichalcogenides. So it includes moly disulfide, also tungsten diselenide, and related compounds. And the reason that we're interested in these 2D transition metal dichalcogenides is because they may enable an extension of physical scaling below the 3 nanometer node, right? And the reason for this is shown on the figure at the lower left. So this again is comparing the carrier mobility of silicon to that of transition metal dichalcogenide monolayers. You can see the mobility of silicon is dropping off, but the mobility or the transport properties of our TMD monolayers are quite good even at thicknesses below 1 nanometer. So that sparked a lot of excitement in incorporating these materials in future generation integrated circuits. Another motivation for 2D materials is what's currently going on, which is a change in the geometry of our semiconductor transistors. So as I mentioned previously, the current technology node is based on FinFET structures, right, which were these vertical fins. If you want to stack transistors even closer, the next geometry that's currently under development are these nanosheet transistors. So it's shown in the upper right. So you can stack individual sheets of your semiconducting material and then wrap the gate dielectric all the way around the individual sheets. That provides better electrostatic control of the device. In addition, if you have sheets that are only 1 nanometer thick, now you can stack many more of those sheets on top of one another. And that way you can increase the drive current of your individual devices. And finally, another thing that's of interest is to stack P-type and N-type MOS transistors on top of one another. Right now in like FinFET geometries, they're positioned laterally on a substrate. But if you want to get an even higher density of CMOS devices, you want to stack the P-type on top of the N-type or vice versa. And that's something that you may be able to do with 2D materials. So all of the properties and the applications that I talked about are obtained using monolayers or single layers of transition metal dichalcogenides. So how do we get monolayers? So the most common technique is to exfoliate layers or flakes off of bulk crystals. So you can go online, purchase a bulk crystal of moly disulfide, and use an adhesive like Scotch tape to pull off a layer of moly disulfide. And if you do this enough times, you're going to end up with a region that's just a single monolayer. So this ability to fabricate monolayers just by using Scotch tape and a chunk of moly disulfide has really made the field accessible to a wide variety of researchers. So that's been the big positive thing about the ease at which you can fabricate a monolayer TMD if you have a bulk crystal. The problem is that it's not a very scalable approach. And the reason for that is it's very difficult to make large bulk crystals of something like moly disulfide or tungsten diselenide. The technique that's most commonly used is chemical vapor transport. This is a synthesis process that's carried out in a quartz tube, a sealed quartz tube. And typically the sizes of the crystals that you can get from chemical vapor transport might be on the order of 1 inch, maybe 2 inch in size, as I'm showing here. But they're irregularly shaped, and they're really not viable for a device technology. So instead, there's been a lot of focus and a lot of interest on using vapor phase deposition methods. And the most popular technique that's used to deposit monolayer films of TMDs is chemical vapor deposition. So just to show you this technique, for those of you who aren't familiar with it, you start off with a substrate where you want to deposit your film. And then you have source molecules that contain elements of the film that you're depositing. You introduce these in the vapor phase. They get heated as they approach the substrate. They start to react and decompose. And then you end up nucleating islands on your substrate, in this case, TMD islands. Now, in order to get a film that has few grain boundaries or other defects, we need all of these islands to be well aligned on the substrate. And to do that, we use a process called epitaxy. So in the case of epitaxy, you're using a substrate that has a similar crystal structure, similar spacing of atoms, and you're using that to template the orientation of the film that you're depositing, right? So you start off with these islands that nucleate on the substrate. They grow in size. You can see from this animation that they're starting to come together to form a coalesced film. And then in addition to having the single layer, you may also get some bilayer islands that start to form. Those are the little additional white islands that have formed on top of the pink. So the focus of our work has really been on studying the fundamental mechanisms of epitaxial growth of these transition metal dichalcogenides with the goal of being able to develop wafer scale films that are single crystalline, have as few defects as possible, and that are going to be suitable to advance the technology towards device applications. Now, when we're considering an epitaxial process, there are a few things that we need to think about. The first is just the physical properties of the elements that comprise the film. All right, so we have the transition metals. We have things like molybdenum and tungsten. Those are materials that have high melting temperatures, right? They have very low vapor pressure. As you can see on the figure at the top right, the vapor pressure of molybdenum is very, very small, and unless you get to very high temperatures in excess of about 2000 degrees C. In contrast, we have the chalcogens, things like selenium and sulfur. Those have low melting temperatures and high vapor pressures. So if you just compare the vapor pressure of selenium to molybdenum at a given temperature, you can see that there's orders of magnitude higher vapor pressure of something like selenium compared to molybdenum. Another thing that we have to consider is the growth temperature that we're going to use. And there's a general rule of thumb for epitaxy that the growth temperature should be greater than about half the melting temperature of the material. That's just based on the bond strength, right? You want the atoms to have enough energy so they can move around on the substrate surface and find a location, a lattice location where they can incorporate in order to have an epitaxial film. And this is based on, you may be familiar with like the zone model of microstructure development. So it comes out of that zone model. So if we just consider that for something like moly disulfide, it has a melting temperature of 1185 degrees C. So this indicates that our growth temperature needs to be greater than about 600 degrees C. The final thing that we need to consider is the sticking coefficient. So the sticking coefficient is basically the fraction of atoms that hit the substrate surface that are going to stick and be incorporated in the film. And that's related to the vapor pressure. So for elements like molybdenum and tungsten, the sticking coefficient is close to unity. Basically, every molybdenum atom that hits the surface is going to stick. In contrast, with selenium and sulfur that have high vapor pressures, their sticking coefficients are very small. And there have been some measurements done in the literature as shown here. They have very low sticking coefficients, particularly at a temperature of like 600 degrees C. So these kind of set the conditions that we need to use for TMD epitaxy. We need to use high growth temperatures. We need to have a great excess of chalcogen compared to our metal, just to have enough of the chalcogen around to get stoichiometric growth. And then we also want to grow at a low growth rate so that we're just depositing a single monolayer on our substrate surface. So the technique that we use at Penn State is metal organic chemical vapor deposition. So in metal organic chemical vapor deposition, or MOCVD for short, the precursors that we use are metal hexacarbonyls, like tungsten hexacarbonyl and molybdenum hexacarbonyl. And then in our process, we use hydride sources for the chalcogens, hydrogen sulfide and hydrogen selenide. And these are photos of two MOCVD systems that we have in the 2D Crystal Consortium facility at Penn State that we use for TMD epitaxy. They both can accommodate a single 2-inch diameter wafer, so we can grow on wafer scale substrates. The vertical Coldwell reactor that I'm showing has a stainless steel chamber, and we have optical ports where we have an in situ spectroscopic ellipsometer, and that enables us to monitor the coverage of the surface as a function of time. So it gives us some way to monitor our growth process. And at the bottom, this is just a snapshot of the conditions that we use. So as I mentioned, we use high substrate temperatures in the range of 800 to 1,000 degrees C, moderate reactor pressures. We use hydrogen as the carrier gas. We use a very low flow rate of the metal precursor. That is what controls the growth rate. And as I mentioned, we want to grow very slowly, so we just get a single monolayer. But then we have to use a high chalcogen to metal ratio because of the differences in the sticking coefficient. And using those conditions, we have growth rates on the order of about 1 to 3 monolayers per hour. And as I mentioned, we grow on 2-inch diameter sapphire substrates. So substrates are an important thing for epitaxy, right? You're using the substrate to template the orientation of your film. So there are some things that you have to consider when selecting a substrate. So the substrate needs to have a high thermal and chemical stability in the growth environment. It also has to have a low lattice mismatch to the film that you're depositing, right, in order for it to serve as a template. And then finally, it has to be commercially available, ideally in wafer scale sizes at a reasonable cost. Now, there are a variety of different options for substrates for TMD epitaxy. We've focused on using C-plane sapphire, as I mentioned. And the reason for that is that sapphire is very chemically and thermally stable at high temperatures. Also, it has hexagonal symmetry, which is similar to the transition metal dichalcogenides that we're depositing. Now, if you just compare the lattice constants of moly disulfide and sapphire, that would indicate that there is a pretty large lattice mismatch, about 34%. However, there's commensurability between the lattices, and that significantly reduces the effective mismatch. So it makes sapphire a good substrate to use for TMD epitaxy. Another problem that's encountered is the orientation of the TMD domains. So if we just consider a flat C-plane sapphire surface, if we start nucleating the TMD domains on sapphire, we find that there are two orientations that are energetically similar. These are referred to as the 0-degree orientation and the 60-degree orientation. That's just the orientation of the TMD relative to the underlying sapphire. Now, if we start nucleating nearby domains and we think about how they're going to coalesce and what type of grain boundaries might be formed, what we see is that if we have domains that are oriented in the same direction, when they grow and they come together and they coalesce, they can do so without forming a grain boundary. And that's ideally what we want to have happen in our process. If we have oppositely oriented domains, whenever they grow and they coalesce, they form an inversion domain boundary. It's also referred to as a twin boundary. And this type of grain boundary has metallic character. So it introduces conducting paths into our semiconducting layer, which is generally undesirable. So our interest really is to be able to control the orientation of our TMD domains so that we minimize the number of inversion domains that we're forming. So let me tell you a little bit about the process that we use for epitaxy. And specifically, this is an example for tungsten diselenide growth on C-plane sapphire. So we developed this three-step process. We start out using a high flow rate of the tungsten source. And I should mention that we're carrying this out under a constant flow of hydrogen selenide. So we always have the selenium or the chalcogen present in our growth environment. So we initially use a higher flow rate of the tungsten source to help supersaturate the vapor phase and drive nucleation on our substrate surface. And we end up with these tiny little clusters of tungsten diselenide. And then we switch the tungsten source out and we just allow the substrate surface to anneal or ripen under a flow of the hydrogen selenide. And these little clusters will diffuse around and they'll form small, tiny little triangular domains. And then we can reintroduce the tungsten source, but at a lower flow rate, so we can laterally grow the domains without getting additional nucleation occurring. So for example, this is an illustration just showing how the domains change in size as we vary the lateral growth time. So we're increasing the time of that lateral growth step from 5 minutes up to 45 minutes. And you can see at 5 minutes, we have these triangular domains, right? They grow in size, they start to coalesce, and then after about 45 minutes, we have a nearly fully coalesced monolayer. I should point out that the lighter color regions, that's the underlying sapphire. So the gray regions are the tungsten diselenide. And you can see that after 45 minutes, we still have a few little holes that haven't filled in, but we also have some bilayers, and those are the darker triangles that appear. You can see that more clearly maybe in the 30-minute image. So we can track how the coverage of the monolayer and the bilayer change with time. But what I want to point your attention to is the orientation of the domains. And you can see that more easily for the 5-minute and the 20-minute condition before they've started to coalesce. So if you look at the orientation in this case, you see these two oppositely oriented domains. These are the 0-degree and the 60-degree orientations that I mentioned earlier. And in this case, they're present at a ratio of about 50-50. So we would expect this film to have a fair number of these inversion domain boundaries. But we modified the growth conditions a little bit. So we increased the growth temperature from 800 up to 1,000 degrees C, and we increased the flow rate of our hydrogen selenide even further. And what we found is that we got a preferential orientation for our tungsten diselenide domains. And I've color-coded them using red and blue in this case. So the red domains have the 0-degree orientation, and the blue domains have the 60-degree orientation. And you can see that there are many more red domains than there are blue domains. So we have a clearly preferred alignment for our tungsten diselenide domains, which is what we want in order to minimize inversion domains in the film. So when we saw this, we were very excited, but the question is, what's giving rise to this preferred orientation? Now, I should mention that the sapphire substrates that we use aren't atomically flat. They have steps on them, right? And this just comes about because of the way that the wafers are cut from the sapphire bowl. So you typically cut the wafers at a slight miscut off of a major crystallographic plane, and this results in steps, periodic steps on the surface. So this is an AFM image of our sapphire surface with steps and terraces. You can see that the terraces are about 100 nanometers in size. The steps are maybe about 0.2 nanometers tall. So very small steps across the surface. And it's previously been shown that steps on the sapphire surface can serve as sites for nucleation of our TMD domains. These are just two examples from the literature for molybdiselenide and then also for molybdisulfide, where they saw a preferred orientation. So we wanted to take a closer look at this, and we can do this using our three-step process. So we can stop the growth right after nucleation and ripening when we just have these tiny little islands, and we can look at where those islands form relative to the step edges on our sapphire. So this is an AFM image of the surface. You can see the steps on the sapphire, right? They're sort of like the vertical lines. And then the tiny little dots, the white dots, those are the tungsten diselenide domains that have nucleated on the surface. And I've added some white arrows to kind of point them out. Now, if we take a look at the location of the nucleation relative to the edge of the step, what we find is that the majority of the tungsten diselenide domains are nucleating at the step edges, right? And this is something that's not unexpected in epitaxy. If you just think about the fundamental mechanisms that occur and the potential energy landscape associated with diffusion on our step sapphire surface, you can see that we have adsorption occur, and then the adsorbed species can diffuse around on the surface, so they can diffuse around on the terrace, and then once they come to a step edge, they're going to get trapped by the Ehrlich-Schwabel barrier. So this is an energy barrier that exists anytime you have a discontinuity in the surface, that you're using for epitaxy, and it can trap the atoms as they migrate across the surface. So they can get trapped at the top edge of the step, but the more energetically favorable location is for them to become trapped at the bottom edge of the step. So we wanted to take a closer look to see exactly where the nucleation was occurring, and we used our three-step process again, but now we extended the lateral growth time a little bit longer so that we got triangular shaped domains. And that gave us a way to see exactly where the nucleation is occurring on our step sapphire surface. And again, I've color-coded the domains, and you can see that the majority of the domains are nucleating at the step edges, but in particular, they're nucleating at the top edge of the step, right? So again, I've color-coded the red for domains that are nucleating at the top of the step versus blue for those that nucleate at the bottom edge of the step. So the presence of steps on the sapphire surface gives rise to this preferred orientation. And if we can control it so that most of the domains are nucleating either at the top or at the bottom of the step, that gives us a way to reduce inversion domains in the film. Now, the question that we had is, what we see experimentally is that the domains are nucleating at the top edge of the step. They're not nucleating at the bottom edge of the step, which is the location that you would expect them to just based on a general Ehrlich-Schwabel barrier type of model. So we wanted to understand this more, and we reached out to our theory colleagues in the 2D Crystal Consortium, Vin Crespi and Audrey Van Duyn, and they did some DFT calculations to take a look at the location on the sapphire surface where we might expect nucleation to occur. So in this model, this is a cross-section of the sapphire surface where we have steps, right? We have these atomic steps. And as the sapphire that we receive is terminated with hydroxyl groups. So there are hydroxyl groups that are terminating the surface. But when we take this sapphire that's terminated with hydroxyl groups and we put it in our MOCVD reactor and we heat it up under hydrogen to 800 degrees C, the hydrogen reacts with the hydroxyl groups and it removes them from the surface in the form of water. So we're reducing the surface and the surface becomes aluminum terminated. So we're changing from a hydroxyl terminated surface to an aluminum terminated surface. And they took a look at this process of hydroxyl removal as a function of location on our step sapphire surface. And what they found is that the location where hydroxyl group removal is most favorable is the top edge of the step. And the location where it's least likely to occur is the bottom edge of the step. So this indicates that depending on the growth conditions we're using, we can have a mixture of hydroxyl termination or aluminum termination of our sapphire surface. Now, if we have aluminum termination, the aluminum atoms are going to be very reactive, particularly to selenium that's present in our growth ambient. So we would expect the aluminum terminated sapphire surface to become passivated with selenium. And that's actually an important thing if we have van der Waals epitaxy occurring, if we don't have chemical bonding between our 2D film and the sapphire surface. So we assume in this model that we have selenium passivation of the sapphire surface when we have an aluminum terminated surface. And we have evidence for this selenium passivation layer experimentally from a cross-section STEM imaging and EDS that I'm showing here. So in the model, they're assuming that when we have aluminum termination, the surface is going to become passivated. And so they can consider two different types of steps that we might have. In one case, we have not completely removed the hydroxyl groups from the bottom edge of the step. So there's still this oxygen remnant at the base of the step, the bottom edge of our step. So we call that a mixed selenium-oxygen step edge. In the other case, we have completely removed all the hydroxyl groups, and we have a fully selenium terminated step. And what we find is that the tungsten diselenide doesn't like to nucleate in regions where there's still some hydroxyl groups present. So as a result, when we have hydroxyl groups that are present at the bottom edge of the step, then the most likely location for nucleation to occur is the top edge of the step. However, when the sapphire surface is fully selenium passivated, then the bottom edge of the step is going to be the preferred location. So this is what the model predicts. And fortunately, the experimental results support that model. So this is a series of AFM images for tungsten diselenide grown as a function of reactor pressure. So we're increasing the reactor pressure from 200 torr up to 700 torr. And that increases the chemical potential of hydrogen and hydrogen selenide in the growth ambient. So it's more likely at higher reactor pressures for us to have a fully aluminum terminated surface that's passivated with selenium. And what we find is that as we increase the reactor pressure, the orientation of the domain switches. So it changes from being 0 degree at low pressure to being 60 degree at high pressure, which is consistent with the model predictions just based on the step chemistry. So the upshot of this is not only are the presence of steps important, but also the chemistry of the sapphire surface is also very important. And that's going to vary depending on the type of growth technique that you're using and also the particular conditions that you're using. So now let me just switch and tell you a little bit about the properties of our TMD monolayers. So if we extend the lateral growth time out, we can coalesce all these domains and we can get a nearly fully coalesced monolayer across substrates that are 2 inches in diameter. If we do in-plane X-ray diffraction, which is shown in the top figures, this is an in-plane phi scan. So it measures the symmetry of the substrate peaks and also the film peaks. And we can see that the tungsten diselenide is growing epitaxially on the sapphire as we expected. If we measure the full width at half maximum of one of our phi scan peaks, we get a value around 540 arc seconds, which is pretty good for a heteroepitaxial film that's only 3 atoms thick. Also, if we do variable temperature photoluminescence measurements, we see luminescence at low temperature that's dominated by excitons. And we have a very low defect-related or defect-bound exciton emission, so indicating that the level of defects in our films are not too high. So they look good overall in terms of the properties. And then in addition to the tungsten diselenide that I talked about, we can also grow sulfides using this process, so tungsten disulfide and moly disulfide, as well as moly diselenide. And the films all grow epitaxially on the sapphire surface. So now let me just focus in a little bit on the tungsten disulfide films. So we wanted to take a closer look at the microstructure of our monolayer films. And to do this, we're going to use TEM, but we need to remove the film from the growth substrate. We do this using a water-based transfer process. So we coat the sample with PMMA and then scratch around the edges and immerse the sample into either water, DI water, or maybe a dilute sodium hydroxide solution. And when the water gets underneath the TMD film at the interface between the film and the substrate, it helps to lift the film off of the substrate because, again, it's just attached by weak van der Waals forces. So we can lift off our tungsten disulfide, and the bottom is just showing a couple of photos where we have transferred a 2-inch tungsten disulfide monolayer from sapphire onto an oxidized silicon wafer, or we can transfer it onto a process device structure or onto a TEM grid. So we worked with our collaborator, Danielle Hickey and Nassim Alem, to do TEM characterization of these tungsten disulfide monolayers. And this is what the AFM looks like for this particular sample. We have a completely coalesced monolayer, and then these little white specks, those are bilayer domains that have started to nucleate. So if we just look at this film using electron diffraction, we see a spot pattern, right? So that indicates that the film is single crystal. If we look at this film using bright field imaging, we see contrast that's just due to bilayers. So you can see clearly the bilayers in a bright field image. But if we do dark field imaging, we can start to see contrast in the monolayer that we don't see in the bright field image. And I want to just point out a few features that I've marked 1, 2, and 3 in this particular image. So if we take a closer look at these TEM images, again, you can see these features. On the left side is just a single area, but if we take a number of these dark field images and we stitch them together, we can form a composite image of a larger area that's similar to the area of the AFM that I showed you earlier. And I should mention that these circular features that you see in the composite image, those are just artifacts from the TEM grid that this monolayer is sitting on. So let me just point out a couple of features that are present in these monolayer films. So we have the bilayer domains that show up with a very bright contrast in the dark field image. We also have some holes in the film. So these are either regions where the film hasn't completely coalesced, or maybe they're holes that form during the transfer process as we pull the film off of the substrate. And then we have these additional features which have a darker contrast. So they're embedded in the monolayer, but they have a darker contrast than the surrounding region in the monolayer. And you can see if you look at this composite image that there are a number of these small regions that show up in the monolayer. Now, when we initially saw this, we thought, oh, these are inversion domains, right? Because we still have some of our domains that are misoriented, right? So we expected to have some inversion domains present in our films. But our colleagues did some very detailed TEM analysis of the grain boundaries associated with these features that have a darker contrast. And what they found is that these are actually not inversion domains. The orientation of the tungsten disulfide is the same on both sides of one of these grain boundaries. Instead, these are translational line defects. So they're defects that arise when you have domains that are oriented in the same direction, but they're just slightly or they're slightly offset, even by like a subunit cell length distance. So they're just slightly offset from one another. And as a result, you don't have a perfect stitching together of the lattice. You have, some vacancies that are present, and that gives rise to these translational line defects. So this is another type of defect that is present in monolayer films, in addition to the inversion domains that I mentioned earlier. So now let me finish off just by talking about the transport properties of these films, because I motivated this by saying that we're interested in these TMD monolayers for field effect transistors for future generation integrated circuits. So we started off just comparing the transport properties of field effect transistors fabricated using the MOCVD grown monolayer films and comparing the performance to devices fabricated using multi-layer exfoliated molydisulfide. So these are films that are exfoliated from a bulk crystal, right? And I should mention, this is some work done by my colleague Saptarshi Das at Penn State. So they compared the transport properties of the two different types of molydisulfide. And what they found is that the carrier mobility was very similar for the MOCVD film and the transistor fabricated using the exfoliated molydisulfide, similar subthreshold slope, and other characteristics. So the upshot is that the transport properties of the MOCVD grown monolayers are very similar to what you would get from exfoliated flakes, which is sort of the benchmark right now in the field. So the nice thing about having wafer scale monolayers is now you can start to make a large number of transistor devices and get some statistical data on their performance. So this again is some work from my colleague Saptarshi Das's group, where they fabricated several hundred molydisulfide and tungsten disulfide FETs with channel lengths varying from 5 microns down to about 100 nanometers. They saw very low device-to-device variation. So that enabled them to do some statistical analysis of the device performance. And the upshot here is that they observe very consistent device performance across these wafer scale films. And then taking that one step further, again, my collaborator, Saptarshi Das, he didn't want to limit himself to a few hundred transistors. Instead, in this particular demonstration, he's making 10,000 transistors, but also stacking layers of transistors on top of one another. So this is a demonstration of a two-tier monolithically integrated circuit where there are 10,000 FETs in each of the tiers, and then there are inter-tier vias that connect them together. And so you can see that now we're taking this this 2D material technology, and we're moving it to the point where we can start doing 3D integration. We can start stacking together devices fabricated using our molydisulfide monolayers. So we're moving towards the ability to make these nanosheet transistors, which is where the 2D materials can really find applications. So this is enabling new stacked 2D device architectures that incorporate high device densities. Okay, so to finish off, I just want to summarize where things stand. So epitaxial growth is a really promising approach to be able to produce wafer scale monolayers of 2D materials. However, understanding the fundamentals of the synthesis process are really key. As I showed you, we need to control both the structure of the substrate that we're growing on as well as the chemistry of the substrate surface. They're both critical in order to get films that have high crystal perfection. We use MOCVD growth. So MOCVD is a technique that's compatible with semiconductor manufacturing. It's widely used for 3.5 films. The next step here is to scale this up to a multi-wafer system so that you can deposit films on a number of wafers in a single run, as well as incorporating in situ monitoring to be able to get even tighter process control. But what I want to emphasize is that this field is really still in the early stages. There are a number of things that have to be worked on. One of which is doping. We need to be able to control the material to make it N-type or P-type. That's an area that's just really starting. Also, there's a lot of interest in heterostructures, TMD heterostructures, as well as selective epitaxy and looking at alternative substrates to sapphire. So I just, encourage you, if this is an area that you're interested in, it's really, I think it's still starting off, still in the early stages. So to summarize, currently we have films, and I would characterize them as being nearly single crystal, right? They're well-oriented, but there are still some defects, pinholes, point defects, inversion domains, some bilayers. But I think with additional resources, additional time, and then of course, the sweat and the tears of graduate students, I think we can really advance this. I did not have blood in there. I just had sweat and tears. I think, there's still a lot of room to improve these materials even further. So with that, I want to acknowledge the people who did the work, the members of my research group, and also some of the staff scientists in our 2D Crystal Consortium facility that I've listed here, as well as the great collaborators that I have who contributed. And finally, the National Science Foundation for funding this work through our 2D Crystal Consortium facility. And I want to just put a plug in for the 2DCC, if you'll allow me. So as Zach mentioned, this is a user facility for the synthesis of 2D layered materials. So we have several different facilities. We have a thin films facility that includes the MOCVD that I showed, but also we have really nice equipment for MBE growth of layered chalcogenides. We also have a bulk crystal growth facility that can fabricate a whole variety of different bulk crystals of chalcogenide ternary alloys, doped crystals. And finally, we have a theory and simulation facility that helps to support the research that we do internally to improve the properties in the material. As I mentioned, this is a user facility, so we've had a number of users primarily located in the US, but I wanted to mention that we also host international visiting researchers and scholars. So, if that's something that's of interest to you, please get in touch with me or check out the website. I listed it down here. So with that, I'd like to thank you for your attention, and I'd be happy to answer any questions that you might have.
All right. Thank you for the wonderful talk, Joan. Are there any questions for Joan? If so, please use the microphone. Yes.
Hi, I'm Zachary from Barcelona. Thank you very much. It was a very nice talk. And I think I recognize one of my former students in the last picture, Myung-Gok Kim. I think she was working with you.
She was a visiting scholar.
Yeah, I was working with her in Tokyo. And she's a brilliant student. So I'm very happy that you were able to work with her. I have a question regarding the field of application of these new materials. I'm also interested more in neuromorphic computing, but also in new materials. And I was under the impression that there was a lot of untapped potential, not necessarily in changing materials, but in making more specialized chips. And this is something, for example, that some companies such as NVIDIA are orienting themselves using, I don't know, tensor cores, which are able to do great matrix multiplications and so on. And my personal impression, and I would like you maybe to comment on this, was that with these new materials on hand, wouldn't it be the ideal moment to actually, rather than trying to reproduce what silicon is doing, but better, trying to also go toward these new applications, for instance, computing at the edge or reservoir computing or whatever else?
Yes, that's an excellent point. So my collaborator, Saptarshi Das, he specializes in device fabrication, and he has been doing a lot of work looking at specialized devices and circuits for edge applications, Internet of Things. Yeah, I think that's actually one area where 2D materials can really play a role, because those particular applications require low power, energy efficient electronics. And that's where I think the 2D materials can shine. So yeah, thank you for bringing that up. I totally agree with you that I think that's an important area.
We have a question right here.
Thank you very much. This is...
yeah, please go ahead. Yeah.
This is Mariam Ibrahimi from Canada, Lakehead University. My question is in the structure that you showed, the defects, the inversion area, do you have data on local spectroscopy, scanning tunneling spectroscopy to differentiate in that sense? Thank you.
So yes, that's a great point. Using scanning tunneling microscopy in order to look more closely at the defects that we have. And STM is particularly good for point defects, right? So one of the challenges that we have is that we're growing on sapphire, which is insulating. So we either have to transfer the films to a conducting substrate or maybe grow on something like graphene that is more conductive. So we've done some work in that regard, but that's one of the problems that we have in just using STM more frequently on our films is that if we transfer them, there's some residue that's left from the transfer process. So it's really difficult to get a nice clean surface for STM. But certainly STM is a great way to look at these defects and especially point defects. Yep.
You have a question here?
Hi, Joan. Great talk.
Thank you.
David Strada from Boise State. I'm curious about the aluminum termination. Is there anything very specific about aluminum in terms of the energy barrier at the step edge? Or can we kind of reproduce it with other transition metals where we might get better control of that nucleation?
So, so you're talking about just the aluminum termination and whether we can modify that with the transition metal. So yes, there's some work from a group in Israel where they have observed that there may be some tungsten substitution of the sapphire surface, and that can be very beneficial in terms of epitaxy, of just promoting epitaxy. So I do think, just beyond what I've talked about with the selenium passivation, I think there are even more things that could be done to look at the chemistry of the sapphire surface and ways to make it a little bit more robust so it's not so specific on the growth conditions that you're using. Yep.
Other questions? Yes, here, and then in the back after. Oh, please.
Hello, very nice talk. I was wondering if there is a way of controlling the position of your domains on the film, and if there is an impact on the electrical conductivity. And another question is related to the fabrication. I imagine, Jan, that you are using electron beam lithography, but how do you recognize, how do you position or contact specific exfoliated films?
Oh, okay. So let me answer the first question, which was, how do you control the position of nucleation on the sapphire surface?
Of the domains.
Yeah. So definitely, as I showed, steps play an important role in that. So one way to do that is to control the density of steps by using substrates that have a higher miscut. They're going to have a higher step density. So there's been some work looking at that, as well as other orientations of sapphire. So I think there, I just really limited my talk to C-plane sapphire, but there are other orientations that may give you even more control over the location where nucleation occurs. And then your second question had to do with
the fabrication for contacting the exfoliated films.
Yeah, so the films that my collaborator is working with, these are large area films. So he doesn't have to worry so much about locating a flake because he's transferring areas that might be a centimeter or even up to 2 inches. So yeah, so I think in that case, having to locate the flake on the substrate is not as critical, and that's one of the benefits.
And what about the contamination with the PMMI? Maybe there is a contamination. You didn't talk about that, but
yeah, that still remains a big issue in the field. Is just any potential contamination from the transfer process.
Have you tried another technique for transferring?
We've tried like a PDMS stamp, which is another approach that's used to transfer. That also leaves some residue too, though. So I think this whole transfer process is another field of development that needs to be done.
Okay, thank you.
We'll take this last question here.
Thank you for the talk. It was very interesting. Well, my question is about what are the challenges to grow heterostructures besides the ones that are in growing the monolayers, because well, actually there is a lot of like hype in heterostructures, and also if your research group started to address this challenge.
Yep, that's a great question. Yeah, there's certainly a lot of interest in heterostructures, TMD heterostructures. We've started doing a little bit of work on that. The challenge again is controlling nucleation of the second layer, right? And getting the second layer to grow laterally and not vertically, so that you don't have, a lot of vertical domains growing upward. That can be challenging, but again, I think that's an area that's really just starting right now. I think that, if once we understand the process a little bit better, it's going to be possible to fabricate large area heterostructures as well. So,
All right, with that, let's thank Joan once more. Thank you.
thanks.
No, right here, right here. Yeah, there's a step right here. All right.
Nice to meet you. This is Marianne Redwing. I'm an SPM for Central. I'm long-term student, so I'm staying right here. We do 1D and 2D materials, organic based, and recently I just started also basically inorganic. Like for the field problem, these are our highway, but we don't do CBD. We do everything else.
Right, yeah. No, I mean, if you'd be interested, we do grow on graphene, which is a suitable substrate to use for,
That's very delighted. So I have worked on various places. So Waterloo, I worked with John in another university. So I'm trained as a surface scientist.
Okay,
For the unit growth, and then I worked in Germany, UC California, also with postdoc. So my background is surface science.
Yeah, no, if you're interested in